Hello, everybody. Now I've unmuted for starting our webinar. So before we start, you will have an introduction by Dr. Maria Grazia Giuffreda. And I leave her the space now. Please, Maria Grazia.
Yes, thank you very much for joining us in this webinar. And the reason of this short introduction is because those of you that saw my email yesterday evening advertising the deadline for submission of proposals, they all of a sudden have probably or might have been surprised to see that we open again our CHRONOS Tier-0 call for proposal. The reason being that apparently there will be no call 25 led by the PRACE ASBL as it used to be in the past years up to now. And rather than simply cutting out completely the possibility for a researcher in Switzerland and in Europe and all over the world to apply for a Tier-0 call, we decided to reopen the CHRONOS call for proposals. The CHRONOS call for proposal is not identical to the national call, so I strongly advise you to actually go on our webpage and read the instructions there. But actually what Luca is going to present in his technical report for submission of proposal will be relevant also for the CHRONOS call, because our CHRONOS call is very, very similar to the what used to be the PRACE Tier-0 call for proposals. So I will actually leave Luca to go on with this webinar. I just wanted to give a short introduction to clarify the CHRONOS call, but I will be also here in the room. So at the end of the presentation, if you have questions, we will be more than happy to answer you. So I hope you will enjoy the webinar.
Thanks a lot, Maria Grazia. So thank you all for joining. And let's get started. As I anticipated at the beginning, we will leave plenty of time at the end of the presentation for questions. Maria Grazia will be also in the room for your questions related to the recent CHRONOS call for proposal. You can also unmute yourself and ask questions. You have the chat to ask questions if you don't want to talk directly, so I can also monitor the chat, but probably it is more efficient if you wait till the end of the presentation to pose your questions until you will have seen all the slides. The presentation will try to cover the topics of the technical report that are relevant, as Maria Grazia said, for the different calls that we have opened. So this should suit your needs for the two upcoming deadlines. Let's then get started with the presentation. So the outline is as follows. We will start with the user lab allocation schemes, in particular the different calls to let you access the user lab. And in this case, as Maria Grazia pointed out, these are national calls for proposals, as we don't have now the PRACE call for proposals for this time. And the main part of the presentation will be on the technical report. So we will show the main points of the proposal templates for the calls for proposals and focus especially on the scaling experiment. So the main part in order to provide the information how to request your allocation. The end of the presentation will be an example step by step of a technical report for your proposal submission. So let's go on with the user lab allocation schemes. Now, the access to the user lab is becoming, let's say, more demanding because we grant at CSCS world-class resources to all researchers in Switzerland. And usually HPC computing systems are oversubscribed. So there is a high competition that keeps also the quality of science high. And the granted resources, in fact, depend mainly on the quality of the proposals from the scientific point of view. However, the technical part is a necessary part to fulfill in order to be able to run. So the scientific researchers, they can access CSCS computing resources for free, but they need to submit a project proposal that includes a technical report. So the scientific evaluation is performed by international experts, so it is a peer-reviewed submission. And the technical feasibility is reviewed instead by CSCS staff, so the technical staff at CSCS, me, my colleagues in general. Now, how many calls do we have? So these are the national calls for proposals at CSCS. The first one, if you have never accessed CSCS resources, is for sure the preparatory project. Preparatory projects can be submitted at any time for users who need to do the following. Either you need to port and test your code on our production system before applying for a real production project, or you just need to generate a mandatory technical report for your next production project proposal. Another call is for development projects, which are meant to work on codes and algorithms for development, of course. In case you ask more than 36,000 node hours, then you have to go as well to the scientific review, not only the technical feasibility. For less than 36,000 node hours on the Cray XC50, so the GPU nodes of PITSTINT, you are going to be subject to the technical evaluation only. You can find more details on the different calls for proposals in the link that I paste at the bottom of the page under the main CSCS website, User Lab Allocation Schemes. Then let's go on to the main calls for proposals, that is the production projects. Production projects target simulations for a specific scientific investigation. Production projects can be submitted twice per year. In particular, we have the deadlines that are in general in the beginning of May and end of October, beginning of November maximum. Researchers can only apply for resources on the hybrid Cray XC50, so you need to submit there your technical report. And the technical report, therefore, as I said, is on the GPU partition. So as I said, it is twice per year. The allocation period starts at 1st of April, 1st of October. So you have to take into account that the procedure of the scientific evaluation plus technical evaluation takes some time. In general, you are notified a bit before the starting of the allocation period. You can find more details anyway, again, on the link that I put here on the page under the main CSCS user page, User Lab Allocation Schemes Production Projects. The next deadline for submission will be May 16, 2022, for the allocations that will start on October 1st, 2022. You can check all the submission deadlines at the link that I paste below. So again, User Lab Allocation Schemes, deadlines for submission. Then the last advertised call for proposal is the CHRONOS Tier-0 call, which aims at scientific projects that need large allocations. So in order to be considered for the CHRONOS call for proposal, you need to prove the use of GPU accelerators on the hybrid Cray XC50 nodes, so the PITSTINT GPU partition. And the project must be a high impact, a challenging and innovative research problem to be addressed by the project. And the code used for the simulations needs to be highly parallel. So the simulations needs to be scalable, and the request for resources needs to be larger than 1 million node hours on the GPU partition of PITSTINT. Again, more information is available under the CSCS webpage, cscs.ch User Lab Allocation Schemes, CHRONOS projects. Next deadline for submitting a CHRONOS project is May 30th, 2022, with the allocation that will start on October 1st, 2022. For the CHRONOS projects, there is a different template with respect to the production projects. You can find the template and the link under the project scope and plan on this page. You can find it as well in the page linked above. And please, before applying and using strictly this template, read carefully the technical guidelines that are linked as well on this page and in the main page on the CS web page. So let's go now to the main part of the presentation. That is the technical report to be included to your proposal for applying for resources. Now, the technical assessment will be done by CSCS staff for the national calls of proposals. And in particular, here we are addressing the production project and the CHRONOS Tier-0 proposals. Projects are technically reviewed in order to assess their technical suitability on the computing system. So the scaling is one of the topics, but there are memory consumption, number of files, visualization and data transfer needs, a lot of other, let's say, important technical details of your project. In order to run your project successfully, it is necessary that the project is technically suitable. For that, we have prepared the project, the proposal templates, but if there is some missing information, still please be aware that you might be contacted by the staff during the review process, the technical review process, to provide more information or to clarify on some parts of your project. Now, let's start with production proposals. The template that we make available on the user portal for production proposals is available as a PDF at a link at the bottom of this page. So under the user portal, user.cscs.ch, you will find it under the technical report section. In particular, here we focus on the part that is dedicated to the research methods, the benchmarks, and the resources justification. So these are sections that are clearly outlined in the template. The technical data, as I mentioned already before, needs to be provided for the hybrid Cray XC50. So it's the Pitstein GPU partition, the GPU nodes. This is, please take it that into account because it is extremely important. Now, let's go with research methods, algorithms, and code parallelization. The section will start with a description of the methods and the algorithms of the codes that you have adopted. You are asked to justify the choices of the code and describe the possible alternatives. And you need to specify whether you are a developer or a user of the code. On top of that, you need to describe the scientific libraries that are employed and which parallelization approach is used by the code. In particular, it is important that you highlight specific memory and input and output requirements of your code. So typically community codes, so codes used by some scientific communities, they publish this information on their websites. So you just need to look for this information and to report them. In particular, if you use a community code, we ask you also to state if you use the standard code or you use a modified, a custom version of the code. And please explain why you cannot use the standard version. And if you're not using a community code, then we expect to have more details in the description of the items that we have pointed out about the algorithms and the methods, because we think that in that case, you might be considered as almost as a developer of the code that you use, or at least you should have deeper knowledge of the code if it is not a, let's say, community one. Then next section is representative benchmarks and scaling. We require all applicants to perform weak and strong scaling tests with the codes or codes that have been selected for the proposal. You need to report the scaling data and in a table and a plot in order to have a visualization of the data for each representative system of your project. You need then, after the scaling is completed, you need to choose the most efficient node count that will be used in your production runs. So you need to select meaningful job sizes in order to simulate the representative systems. And in particular, you should have a short runtime. You are doing, let's say, a scaling test, so you're doing a benchmark, you're not doing a real simulation. You have to select something that is meaningful, but you don't have to spend a lot of resources in order to do that. So typically minutes are the range of time that you need to spend for a benchmark. So the lowest number of nodes where you start your scaling study should be then determined by both memory and time constraints. Time meaning wall time, the clock time constraint. So you would not spend hours just because you want to run on a single node. So if this is a constraint, please just clarify that it takes too much time in order to run on low node counts. Or you might have memory constraints. Maybe you need to distribute your simulation over a certain number of nodes in order to start, and you cannot with a single one. Everything is acceptable. It is important that you clarify that and you specify what you're doing and the reason why you're doing that in the proposal. On the other hand, the highest node counts where you stop doing your scaling study should let you identify what is the scaling limit. So what the scaling limit means, the node size where it doesn't make sense to go beyond. In particular, we give a kind of rough indicator that is the parallel efficiency should not be below the 50%. So whatever you do in production should be above 50% parallel efficiency with respect to ideal scaling. Parallel efficiency means that what you're doing is computation and not just communication. If you go at a parallel efficiency below 50%, it means that most of the time that you're allocating nodes, you're just not computing stuff, but you're doing communication or you're waiting. So it's really wasting resources. That's why this is a rule of thumb, but makes you, let's say, understand that you shouldn't waste resources. Now, on top of that, we introduced in the template a table that you can use as a guideline to provide some what we call workflow parameters. So workflow is the workflow of your simulation, which might start with some pre-processing, the real processing, post-processing. All these steps involve certain parameters like the number of jobs that you plan to run simultaneously on the system, the work clock time of a typical submission expressed in hours, and what is the expected job size of the typical jobs measured in nodes. Then another important thing is the memory per node that you plan to request for the typical job, which is usually expressed in gigabytes. And the maximum number of input files and output files of a job. This is extremely important because especially on our Scratch file system, which is a raster file system, the performance gets worse with increasing number of files on the system. So we need to take that under control. And then it is also important to know the maximum number of files that are accessed simultaneously by your jobs, your typical jobs, and the largest file size together with the library that you use for input and output, which typically are the bottlenecks in simulations, the library for input for I/O. Last but not least, the maximum number of and size of files that will stay on the Scratch file system at the same time. So the Scratch file system is the raster file system that I just mentioned, that is particularly efficient if you use large files with small number of files. And then these are important parameters for us to understand which will be the load on the file system. And you also might know that we have a soft quota on Scratch. So if you go beyond 1 million files on your Scratch, you will be blocked to submit new jobs and you need to clean before going on. That's exactly because we know the performance of the Scratch file system will be affected by a large amount of files. Next step in the proposal template is the batch job summary report. What is that? So a summary report is created at the end of each successful batch job on our system. So an interactive job does not count. because an interactive job does not produce a Slurm output file. Slurm is our schedule manager, workload scheduler. So interactive jobs, the one that you might use for debugging, do not create any report. Anytime you have a Slurm output file, at the bottom of the output file, you should find this report, if, of course, the job exited successfully and was not crashing because of errors. Details on this report are available on the user portal, and they will provide you on more information on what you be able to find in this report. We ask you to provide the batch job summary report for each representative system that you're simulating in production and that you are mentioning in your proposal. So please, in order to provide this batch job summary report, just provide the one that is linked to the job size that you have selected after doing the scaling experiment. So you do the scaling experiment, you decided that a certain node size is the most efficient one, which should be above the 50% efficiency. So more efficient than 50%, hopefully towards the high efficiency of 60, 70, 80% and not towards the 50, in order to waste the least amount of resources as possible. Then you just need to look at the Slurm output of this job and take the summary report that you should find at the bottom of the file. You should please also enclose not only the report, which is not too long, but also the Slurm job ID of the job that you have used to extract the report in the proposal. And that's now the last and important step of the resource justification. So this is the section where you justify the allocation that you are requesting. Now, the request of the annual amount of node hours that is planned for the project is easily computed from the number of nodes that you've used, multiplied by the whole time that the job is taken, expressed in hours, and then you have the number of node hours. You should clearly link this request, this number, to the node hours that have been used by your representative benchmark. So in the scaling experiment, you have done your benchmark with the different node sizes, you selected the efficient one. So you set this one as the reference time, you express this time in hours, you multiply it by the nodes that is needed by this job, and you have this number that should be used then in order to construct, to build all these requests. You can have multiple tasks, and then you will report the multiple tasks, but still the basis of the request should be linked to the benchmark. Then the breakdown of the resource request, as I said, will be based on this, of the initial consumption for the benchmark. Then the request of the project storage as well should be based on the IO pattern that you have posted in the table of the workflow parameters, and should be linked also to the need of storage during the duration of the project. So you should highlight here also if you have requirements for visualization, pre-post processing, development, and debugging. Let's now briefly switch to the CHRONOS Tier-0 call for proposals. As Maria Grazia pointed out, there is a different template, which is called Project Scope and Plan, that is linked on the CSCS website. Although the template more or less covers the same content, the names of the sections are a bit different, and the parts that are related to the technical report are highlighted here, and they are software and attributes, then data, management plan, storage analysis and visualization, and then performance of software. Again, the very important part here again is that the technical data for the CHRONOS must prove GPU usage. So not only you have to perform the technical report on the GPU nodes, but you also prove that you use GPUs on the system. So the batch summary report will help you because they might provide a GPU usage report, but still whatever you can show that the GPU is used is beneficial for your project here. Now, the first section, software and attributes, will describe all the codes that you are using in the proposal. Again, you need to justify the choices, not simply state the choices, and describe what are the alternatives. And in particular, which libraries are required for the production, and if you need analysis, software for analysis. For instance, algorithms and numerical techniques that will be employed, which programming languages are using, and which parallel programming models are used by the codes and the libraries. So just to give you an example, which is not exhaustive, if you're using MPI or OpenMP pthreads together with MPI, CUDA for the GPU accelerators, or you're using OpenACC, and so on and so forth. And last but not least, you should describe the I/O requirements and the strategy of data management. In particular, it is important not only the number of input files or start files, output files, also the frequency of the input-output operations, and the data plan, the strategy for data management. So how do you intend to manage the amount of data that you're generating? Because it is really important that you have a plan to transfer this data, and because the data will be removed at the end of the project. Now, this brings us to the section data management plan, storage, analysis, and visualization. You need to provide a real data management plan with your I/O requirements. So you should also provide a plan that is linked to your project plan with a Gantt chart that shows when and how the data will be moved from the computing center to your local facilities. And then if you have the needs for data analysis and visualization for pre and post-processing tools, you should highlight here exceptional I/O requirements, for instance, of your code. You should also point out if you need additional resources for computing, for archiving, for data repositories. You should announce your intention to submit a request in external calls for proposals that are not directly related to CSCS, for instance, so that we know. And then the part with the scaling experiment as well, that is called performance of software. So you need to provide here data that are, again, representative of the entire workflow of the project, but should be a benchmark small enough to be computed in minutes, in order of time, in a time of the order of minutes. You should refer to the main application code that is used in production, and you should use the scaling data to choose the most efficient job size. The software performance must be clearly linked to the resource request, and again, the data must refer to the hybrid GPU nodes of pth. You should contact us for any concern on the technical data. So rather than leaving anything, let's say, unclear, it's better that you contact us. At the end of this presentation, you will find the link on how to contact us. The strong and weak scaling here in the project scope and plan you should explain as well if either the weak or strong scaling metric is not relevant for your particular scientific case. And you start with the minimum node count that is necessary to run the problem. Again, here you can have limitations due to memory, limitations due to time. You should explain, justify the minimum size that you're for your scaling, if you're not starting with a single node, which is usually the basic unit for our system. And then you should finish with the maximum number of nodes that is suitable for application, depending on the scaling curve, in the sense that you don't want to waste resources. So again, here also, let's say 50% is what we suggest for the production projects. Here in the CHRONOS Tier-0 call, we are dealing with larger and highly scalable projects. So hopefully you are, let's say, scaling much better than 50%. So you should be on higher efficiency. Then you should plot the time to solution, which might be scaled, normalized, or you can plot the speed up, but please clearly state in a table which are the timings, which are the data that you're using, and plot them together with a reference to the parallel efficiency, which is mandatory. In general, just as a let's say, an advice, you can use log-log plots. They can span many orders of magnitude. So plotting your data will be clear to immediately see the scaling behavior of your application. After this overview of the project proposals, the template of the project proposals, let's follow an example step by step. So a technical report step by step. I will use as a driving template the one for production proposals, but the scaling, as you have seen, follows more or less the same steps. So in order to do this small example for your technical report, we use a small benchmark of the CP2K software package. CP2K is a community code used in quantum chemistry, quantum material science simulations. And it's also in the list of the CSCS reported applications that are already available in the module file after you load the module Dane GPU on the system PITS Dane. In the example, we will simulate the dynamics of a water box of 256 water molecules. All the input files, so the basis set, the real input file of CP2K, the potential file, and the Slurm batch script can be retrieved following the instructions on the user portal under the link that I put here under the scaling part of the page dedicated to CP2K. In the Slurm template script that we used, and that is meant to do a strong scaling experiment, so the size of the system is fixed, we simply increase the number of nodes. We use the constraint GPU to make sure that we run on the hybrid cray XC50. And we have selected already 6 MPI tasks per node with 2 OpenMP threads, because this gives us the best performance on different number of nodes. A description of this example technical report that we are presenting here is also available on the user portal at the link indicated in the page. Now, for the scaling experiment, we start with a small size, with the smallest possible number of nodes, that is 1, because the small size of this example allows us to have very quickly a result also for a single node simulation. The wall time on the single node then will be the reference that we will use to compute the speed up for our scaling study. In particular, the speed up will be computed, then taking the timing for the nodes, for the increasing nodes with respect to the single node, and the efficiency will be the ratio of the different speed up values. So the benchmark speed up versus the ideal scaling. Ideal means linear, so something that grows linearly with the number of nodes in terms of performance or time. Now, when do we stop? We check the speed up until we reach more or less 50%, because we don't want to waste resources, so it doesn't make sense to go beyond that. In particular, for this small example, we decide to choose 8 nodes as most efficient job size that has a 52% parallel efficiency, which is towards the low end. And here you see how you should report the data in a table on the left and a plot of the data in a small plot on the right. If you look on the user portal, you will find not only the template, the PDF template, but also a LaTeX template, which includes a small GNU-plot script in case you want to use that. So here in particular, as I pointed out in the previous page, we start with 1 node, as you can see, and we take the time to solution on 1 node as a reference. So we then double the number of nodes in order to do our scaling experiment. And for each node count, 2, 4, 8, and etc., we take the time and we compute the speed up with the reference of 1 node. In particular, the formula to get the speed up on n nodes would be sigma, so speed up on n nodes is the ratio of the timing on 1 node divided the timing on n nodes. Hopefully the timing on n nodes is faster, because otherwise it doesn't make sense. And so the speed up should grow. In particular, you see here the table speed up is the actual speed up of the benchmark. So you see 1 is the reference. So of course, then if you double, you expect a double speed up, which is not the case. You see 1.63. So you are already below what is a linear speed up, which is the ideal. And growing the number of nodes, you see that we are going farther and farther away from what is the linear behavior. This is clear from the table, but is immediately evident from the plot, because you see immediately what is the ideal scaling, so the linear speed up that you would expect. So if you have 1 on 1 node, you expect 2 on 2 nodes, 4 on 4 nodes, and so on, while the actual speed up is lower than that. And you see on 8 nodes, we are already almost at 50%. 16 nodes, we are already below, far below, so it's 36% efficiency. As I said, the efficiency is easily computed. You take the speed up on the number of nodes, let's say 4 nodes, and you divide by the ideal speed up. So speed up on 4 nodes is 2.71. The ideal one expected is 4. It's easy to compute that we are at 68% parallel efficiency. And the formula for parallel efficiency on n nodes is also highlighted here in the top right of the slide. So eta, I defined that it's the efficiency, and that's the ratio of the actual speed up divided by the ideal speed up. Now, here I said we use 8 nodes. We have chosen 8 nodes. It is a small example, so it's still acceptable. But if you have a large project, it makes sense that you choose higher efficiencies. Like here, it doesn't make sense to choose 4 nodes. It's very small node size. But for highly scalable applications, it makes sense that you choose like 60 and 70% efficiency node counts and not go towards let's say the least acceptable ones. Now, the workflow parameters that you can see as an extract of the template. It's a simple table. Here we imagine to have like 2 tasks in your project, and then for each of the tasks we report what are these workflow parameters. So starting from the number of simultaneous jobs that you plan to run in production, typical workload time, here 6 and 12 hours. You know that we have on Pizza the 24 hours limit for the normal partition. So it makes sense to have restart files. It's also more efficient because anything might happen in the meanwhile. Then typical job size, the memory per node, maximum number of input files, output files, largest file size, library used, and the last 2 lines, the most important ones, maximum number of files on Scratch at the same time, and the size of the files. This is just an example, but it gives you an idea of what to put in this table. And you need to take into account the overall usage of your project. That is not just a single simulation, especially for the last 2 items about the number of files and the size of files on Scratch. And now the batch job summary report. As I said, the Slurm output file of your job will contain the batch job summary report. So the report of a successful job will be appended to that. In this case, we use the job size of 8 nodes. We said we use 8 nodes as the most efficient job size. And then in this case, we will find at the bottom of the Slurm output file, the batch job summary. What is included in this batch job summary? So usually there are the following sections. There is a header, job name, job ID, together with the name of the computing system. There is a timeline. So what is the username? That is the job owner. What is the account, and other details on the time of the job. And then the GPU statistics that report the usage of GPU in percentage, the maximum allocated memory, and the execution time. So please note that the job summary report may not contain the GPU utilization for all the nodes, so that you are aware. And this is an example. This is a job that I've submitted, and then at the bottom of the Slurm output file, you can find this batch job summary report, the version, the name of the job ID, on Dynit, so that's the system, then the header, job information, that is listed as 1 of 3, then the job information 2 of 3, which is the username and the partition, and last, the job information 3 of 3 about the GPU utilization data. So the node name, the usage of GPUs in percentage, the max memory on the GPU, and the execution time on the GPU device. So last but not least, the resource justification. So we will clearly link this request with the node hours of our benchmark on 8 nodes. So again, node hours, simply number of nodes multiplied by wall time in hours. So the scaling benchmark, in this case, was a short example with a small number of iterations. You might have multiple jobs with multiple iterations, so you might need to estimate how many iterations you will need in production in order to complete your simulation. The project might also contain multiple tasks, so multiple sets of simulations, and the annual resource request will need to sum up the corresponding amounts of node hours. So just to clarify in a table, we start with the optimal job that consumed on 8 nodes, 0.4044 node hours, which is computing as all 8 nodes multiplied by the whole time expressed in hours. So 182 seconds divided by 3,600 seconds per hour. Then breakdown of the resource request will be based on this number, 0.4044. And the total request in this specific case will be around 20,000 node hours that you see here. Again, I imagine to have 2 tasks, and then I describe for each of the tasks number of simulations that I will do, the number of iterations per simulation, the number of node hours per iteration, which is the basis of this request, and the total node hours per task. So this is pretty clearly linked to what we have done in the benchmark, and this is pretty easy to follow to reach the final number that we are going to request, that is the sum of the 2 tasks. And with this, we can conclude with a page on the useful links that are the user lab with the information on the technical report, and the link to contact us in case of questions.